Hello and welcome everybody to my talk about software archaeology. What you can see on the picture is the Apollo guidance computer in gold. And on the right you can see the user interface of this computer, which was installed in the lunar lander during the first moon landing in 1969. In the next 45 minutes I will present the history of this computer, many technical details, and some learnings which are still valid today. I'm not affiliated with NASA, even if I wear this t-shirt. I'm just somebody who is interested in software archaeology and software history, and I wanted to give you a quick tour about the fascinating story of this computer. But let's first jump back in time some decades. So the space age actually started with a shock, at least for the Western world. What you can see on the right is a Sputnik satellite. It was launched by the Soviet Union on 5th of October of 1957. It was a shock for the US because it was the time of the Cold War and between the US and the Russians. And satellites have many civilian uses. We use it for TV broadcasting, we use it for weather forecast, but they can have military purposes as well. And so the US tried hard to catch on and build their own satellites. But at the beginning of the 1960s, the Soviet Union was still leading. So in April 61, the first man reached space and entered or orbited the Earth. Does anybody know the name of the first man in space? Just shout. Okay, Yuri Gagarin, you're right. And some weeks later, US President John F. Kennedy announced the popular goal to land on the moon during that decade, so in the 1960s. That was a very ambitious goal. The US had launched some satellites at that time, but no man into space. And it was absolutely not clear how they would reach the moon in 10 years, or to be more precise, in 8 years. So the high ambition was a plus for Kennedy. He wanted to create a national effort with this very hard goal to go to the moon, and he explained that later in another talk. So let's take a look how they did this. The NASA made a first program, the Mercury program, as kind of first epic, and it had the clear goal to get a man into orbit around the Earth. So they started in 1958, just after the Sputnik shock, and this program was already running when Kennedy announced to go to the moon. But they weren't the first to get to this goal, but some weeks after Yuri Gagarin entered space, they were at least partially successful when Alan Shepard was the first American in space in May 61. The first US American in orbit was John Glenn, some months later in February 1962. So at this stage, still the Soviet Union was leading the space race. But the US invested a lot and tried hard to catch up. So the next step was actually to design spacecraft that could land on the moon after Kennedy announced that goal. And we see these two spacecraft on the picture here. The one spacecraft on the left is a command and service module, which flies to the moon and orbits the moon, and then flies back to Earth and enters the atmosphere. The second spacecraft on the right is a lunar module, the so-called LEM. It actually attached to the command and service module first in moon orbit, and then it undocks and breaks down to get quite in moon orbit to kind of fall to the moon's surface. And the upper part of the lunar module, which you see, has a rocket engine to fly back from the moon to the moon orbit and make the rendezvous and the docking again with the command and service module, so the astronauts could enter the command and service module to fly back to the Earth. And that was all what the next program, the Gemini program, was about. So it was an intermediate step and they tested the rendezvous of these two spacecraft, the docking of spacecraft and stuff which is associated with that. There was also a second objective to the Gemini program, which was the spacewalk, the so-called extravehicular activity. Of course, well, it was planned to fly to the moon, to land on the moon, and to walk on the moon. It seems to be very human. I think you need to push a flag into the soil to, well, successfully claim, I've been here. And spacewalk is not easy because space is hostile. You have no air, you have no pressure, it's cold, it's dark. So you needed to develop a spacesuit and develop a life support system so that the astronauts could survive walking on the moon. And that was a crucial result of this program, that the astronauts could survive on the moon's surface. Finally, the Apollo program, most of you might have heard about it, with the successful moon landings, and Kennedy's goal was fulfilled. But he was very right about the national effort. The US administration spent more than, at peak time, more than 4% of the budget for the NASA. And today it's around 0.5%. But they landed on the moon and they put the flag into the soil, which is still standing there, I think. So let's take a look at the various Apollo missions. They have such nice mission patches that you can understand just by looking at the patches what it's all about. We have the Apollo 7 mission. That was the first mission to test the command and service module. They tested it in Earth orbit. And maybe another more important achievement was that it was the first mission with a TV broadcast. So the US was very open about it. They broadcasted every space activity to get the people behind these great investments. It was different from the Russians. With the Russian space activity, they never announced it beforehand, but only if the mission was successful, the public got to know about it. So Apollo 8 was the first which actually went to the moon, and you can see the 8, which is kind of the flight profile of this mission. So they flew to the moon, orbited the moon, and then they flew back. And it was still only the command and service module. And on the next mission, Apollo 9, the lunar module had its first appearance. And they tested all these rendezvous and docking maneuvers I told you about with the real modules in Earth orbit. And you can see also the Saturn V rocket on the patch, which is the moon rocket, which well, brought all this stuff into space. Of course, it was better to test all these docking maneuvers in Earth orbit first, because you at least had a chance to get the astronauts back to Earth if something went wrong. But everything went well, and then they made a complete dress rehearsal with Apollo 10, so the complete mission, everything as in the real moon landing, but they just went down to 14 kilometers to the moon surface, so they didn't really land. That had a good reason, because, well, NASA was quite afraid that if they that the astronauts on these missions would try to land if they could. So they didn't totally trust the astronauts, and they did not provide enough fuel for landing and returning, just to be sure that no astronaut just, well, landed. It's clear, of course, why they were so afraid, because all the credit of the moon landing goes to the first man to achieve that. Who was the first man on the moon? Armstrong, yeah, I already heard it. And, well, most of us may never have heard of Stafford Young and Cernan. So, of course, that was a good precaution of the NASA administration. And so finally we got Apollo 11. The Eagle landed. Eagle was the nickname of this lunar module. And many of you might also have heard about Apollo 13. There's a famous movie Actually, the quote is at the wall just outside. Houston, we have a problem. And on this mission, an oxygen tank exploded. And so the astronauts used the lunar module as a lifeboat. And they returned safely to Earth as well. Okay, so enough of the history. Let's get to the technical details. This is the Apollo guidance computer, as I told you. There were actually two on the Apollo missions. One was in the lunar module, and the other one was in the command and service module. And these computer really guided the spacecraft on their journey. They made all the computations, they commanded the engines and stuff. And you can see what the computer did on this picture. They had slightly different workloads. This picture is from the lunar module, so with the command and service module, slightly different, but not that much. It was matching the duty of both spacecraft. Well, first of all, the computer got a lot of input data from the left side. There were optics instruments and where you could measure star directions. There was an inertial measurement unit which was used for orientation in 3D space. You could measure attitudes and accelerations. And then there was a landing radar to measure the, altitude and velocity during the descent to the surface. So you could measure how far from the surface you are to not crash on the surface. And there was another radar for this rendezvous, the rendezvous radar, that was needed to measure the distances to the command and service module when docking again in the moon orbit. All this data was displayed in the cockpit for the astronauts with the display and keyboard, the so-called DISCI. We will look at that as well later. And then there were various engines which a computer commanded. So there was a descent engine to make the descent to the moon surface, an ascent engine to go back into moon orbit, and some jet commands where you could control horizontal position. Well, and finally, all this data, or they could be received and send some data with telemetry from the ground control in Houston. The computer was designed as an autopilot, so it could flew the spacecrafts alone without astronauts. But the astronauts could take over manual control of the spacecraft and, override the computer. Okay, so now we know what it did. And I brought also some facts about the hardware of this Apollo guidance computer. These numbers are the size in centimeter. So it was not really big. It was a bit larger than my laptop here. But for the 1960s, it was really small. It was one of the first embedded computers anyway. And in the 1960s, normally the computers filled whole rooms or even stories. So it was kind of really a small computer. And it was also a relatively light computer. It only weighed 32 kilograms. It's more than my laptop, I have to admit, but in that area, normally the computers were measured in tons, like the mainframes which were at ground control and computed the flight profiles and flight routes and everything. Weight was crucial for the missions, actually, because the more weight means you need more fuel, which is more weight in itself, which means you need more fuel again. And so everything was optimized in terms of weight. And this computer was very light for that age and for what it could do. The next figure is actually totally comparable to my laptop here. It's 55 watts of power consumption. This was also essential because the AGC was powered by batteries, so they needed to keep the power usage low. And gets a bit more interested with some hardware parameters. The 16, maybe some of you might already guess what it's about. The computer had a 16-bit architecture. So we had 1 bit for the sign, 14-bit for the data, and 1 parity bit to check for hardware errors. That was very advanced for embedded computer at that time, 16-bit architecture. But still 16-bit, that amounts to an integer range from minus 16,000 to plus 16,000. That's not that much, actually. And you might wonder why these figures are equal, and that the reason is that they implemented a ones complement in this computer. Nowadays we use the twos complement. Maybe some of you remember from university, but I'm not going into the details here, how it works. And the integer range was not that essential, actually. More important were decimal numbers. So you had lots of computations and to compute the position in space and the distances to other objects, to the command and service module, and to the lunar surface. And they achieved with this computer 9 digits of decimal numeric precision. That's not more than the electronic calculator I had in school. And they only realized that by using a double word, so using 28 bits. This precision translated actually to around 1 foot, it's 30 centimeters, of precision at navigation. So now imagine you fly to the moon and are in Earth orbit and moon orbit and want to rendezvous with the other module, the command and service module. And there's the airlock, where you can get on between the both spacecrafts, enter the one, and go from one spacecraft to the other. And maybe this airlock is, I don't know, 60 centimeters, and you have a precision, you know your position by with 30 centimeters. That's a lot margin of error, I think. So I'm not really sure if it was, well, just it was still, I think, not easy to land with this computer on the moon surface, but there was no more precision to get from this computer. You're all programmers, I guess, and the programmers which had to build the programs for this computer were restrained as well. So we had 2,000 words, 16-bit words of read-write memory, where all the calculated data should fit in. That's only around 4 kilobytes of data you could use to store computational results like the velocity of the spacecraft or something. And you had, even worse, only 36,000 words for your program code. So all the programs you needed to land and fly and all these things needed to fit into 72 kilobyte. Well, it was mostly assembly language, but I'm not sure Hello World and most modern languages might actually need more space than that. And I'm not using any AI assistant here still. So it's really a great achievement to be able to land on the moon with that computer. The next problem for the programmers, you had a 16-bit architecture. You had 1 parity bit. You had 3 bits opcode to determine the operation. That left you only with 12 bits for the memory address. Well, 12 bits, that's 4,069 words you could address, but we had more than that. I told you about 36,000. So they needed to invent virtual addressing to get around this limitation. So they had some encoded memory addresses which needed to be encoded and decoded to the real physical address in the computer. It was called memory backing back then, but we had the concept later and 30-bit architectures as well to address more than 4 gigabyte of RAM. 2 more figures before we get into simulation. My first own computer, I think, had around 40 megahertz clock rate. The AGC had 2. That was quite fast enough for an embedded computer at that time and for the usage during the moon landing. And the last figure, I already mentioned the telemetry, the data which could be sent to ground control. The data rate was 51,000 bits per second to Houston, to mission control. That's not really Starlink, but it's enough to get the crucial mission data from to Earth and back. So now, I already showed you a picture of this user interface before. It was named DISKey, which is an abbreviation for display and keyboard. But we don't only look at this theoretical picture, but there's a nice simulation on the web. I put the link into the slide, and I'll try to switch to that simulation. There it is. So you can see a simulation of the computer. On the left, the display keyboard for the astronauts, and on the right, some instruments which were in the cockpit as well. And we just assume that we are still on Earth in our moon rocket, and we want to launch the rocket with the computer. So I have to start a program. How do you start a program with this computer? You enter a verb-noun combination. So the computer to take numerical verbs and nouns for the program. So I say verb 37, noun 01, and that means, okay, start the major mode, the major program 1, which is a pre-launch initialization. Okay, so I started it, and now you can see there's a program 1 running here on top, and now we can see that the instruments are calibrated and the program is running. The computer is working here, computational activity. And we switched to another program, program 2. That was actually the pre-launch, major mode pre-launch, which automatically started. But that's a bit boring. We're still on Earth. So let's try to launch the computer and the rocket. And now you can see there are some numbers on the display. The program switched to program 11, the major mode for the Earth orbit insertion monitor. So it's a program to monitor that we get into a nice Earth orbit. And you see these figures here. The display could only, or there could only be 3 values displayed to the astronauts. And this verb and noun combination here, 6 and 62, told the astronauts what the figures meant. So these 3 are the velocity, feet per second, the altitude rate, how fast the rocket goes up, and feet per second as well, and the altitude above the launch pad in nautic miles. And you can see the numbers go up. So now you might imagine there are not only 3 values the astronauts had to monitor and to check, so they could enter other verb-noun combinations. So if I enter verb 82, enter, then there are other values on the display and another verb-noun combination to tell the astronauts what these numbers are. And maybe you recognize here a digit is missing. That's actually a time display, so minutes and seconds to free fall. That's all these things, like verb-noun combinations and what the data told the astronauts, had to be remembered by the astronauts. And therefore, I switch back to the presentation. And therefore, they had a quick reference card in the cockpit, much like we use today for shortcuts in IntelliJ or other stuff. So enough from the hardware. We already saw how the computer worked. Most of you might want to know about the software. The computer had a real-time operating system. It was the so-called executive. And it could handle 7 processes ordered by priority. If there was an 8th process, it had to be discarded, or one of the processes had to be discarded, the job with the lowest priority. This limit of 7 was due to the hardware limit. They couldn't store more of these processes. And of course, it was an engineering decision. They calculated how much processes they need to compute all the programs and to fulfill all the mission tasks. And they came to the conclusion that 7 would be enough and there would never be an 8 process. And unlike nowadays, it was necessary to hand over control to from the process which was running with a new job statement to at convenient places in your programs when all your computations are made and the data is stored, which is called cooperative multitasking. It's a contrast to central coordinator, which transfers the control from one process to another. They already also had hardware interrupts, 11 different hardware interrupts. One example was the T3 rupt. It's a timer overflow, so they had different timers. And when the timer overflowed, so the 5 minutes or 10 minutes or 10 seconds or whatever went down, then the overflow occurred, this interrupt occurred, and the time3 timer was used to schedule tasks which are waiting in the wait list. And if an astronaut pushed a key on the disk key like we did just a minute ago, then that was an interrupt as well, the key rupt 1. Speaking of keystrokes, you could enter the whole state vector of the spacecraft manually. Like if the computer and the data it got from the instruments on board was not really good, then they could correct the data with, or the state vector with data the ground control had or something else. But that required 100 keystrokes without any error. That's not that easy. And so normally this mission was sent from mission control via telemetry. That's where the telemetry was for. That's actually one of the first examples of robotic process automation I know of, because the uplink data equaled the disk key input 1-to-1. So it was just a stupid interface to the disk key interface, the telemetry data, which was sent. And maybe the most intriguing part about the software is the interpreter. They had a virtual machine. It was kind of a gimmick for the programmers. I told you about the assembly language and the memory addressing, the memory banking with the virtual addresses. And the programs for the AGC got a lot easier with the invention of a virtual machine, the interpreter. This virtual machine abstracted from the hardware. So they got some vector and matrix data types which you needed for the computations in space, and some other stuff which was just helpful to program. And it also made the addressing simpler because you did not need to calculate this physical memory addresses because the interpreter did it. And the code for the interpreter could actually be mixed with executive assembly, so you can hand over in one program from assembly code to interpreter code. It was really nice design. So now we want to see the computer in action. There's a great website, Apollo in real time. You can live through the 3 missions, actually, Apollo 11, 13, and 17, with audio, video, and pictures. It's great for anyone who's not old enough, like me, to have been sitting in front of TV when it really happened. Somebody here who watched the real footage on TV? Ah, okay. Nice, very great. Okay, I'm too young, unfortunately. So I will show you 2 sequences just before the landing. Switch the screens. Okay, so I have this website here, and I hope the audio is working as well. Okay, so what did you just hear? There are some statics on the audio, but I think it's nice anyway. There was a program alarm which was the computer was showing. I can show you actually how the astronauts saw a computer alarm. So there's this little light bulb in the cockpit, operational error. So if this went yellow, the astronauts knew, oh, there's a program alarm. Then they had to switch some command or push in some command, and then the number of the alarm was shown in the display. And maybe you heard the astronauts said, give us a reading on the 1202 program alarm, because the astronauts didn't know what the alarm was about. And control center in Houston said, oh, no, don't worry, we are go on that alarm. So just continue the landing. You're already laughing. Why? They know what they're doing, right? Okay, so we jump ahead some minutes, 3 minutes or something, just before the landing. Where go? Same type, where go? 12.1 program alarm. Imagine you're the astronaut sitting in this lander and having program alarms. You don't know what they mean, and you'll need a lot of trust in the ground control to continue the landing. And but I think this guy looks really well, fond of himself, or he looks like he's knowing what he does. So what was this program alarm about? Switch to the presentation. Of course, they were prepared. So what happened during the landing? The guys who were sitting in Houston did know about all these program alarms, but that was also kind of a learning they had during the missions, because there was an earlier missions, simulated mission, and the astronauts got this program alarm 12.1, 12.2, and they aborted the simulated mission. The abortion of the landing, of course, is not that nice, because it was broadcasted in TV and would have been a big humiliation for the NASA. And therefore they talked with the engineers who wrote the software. Okay, what's this alarm about? What does it mean? What do we do if it occurs? And stuff like that. And so the controller or the controllers at Houston had all these alarms written on some paper at their desk and could say, okay, 12.1, go, 12.2, go. Everything fine. But still, what was this alarm about? Well, I told you, 7 processes. Well, there was an 8th one. Shouldn't happen, right? There was an 8th process, and it could not be stored. What did the computer do? It was prepared for these situations. It discarded the process with the lowest priority. The process was erased or never even stored, I don't know. So it just continued with the 7 tasks it had to fulfill, which the computer deemed necessary for landing. And 12.02 was just the same for the interpreter. The interpreter could store 5 jobs. And again, the AGC threw the interpreter job away with the lowest priority. So why did it happen? Why were there so many jobs and tasks? There was a malfunction actually in the rendezvous radar. The rendezvous radar sent some stale data, which didn't match the data which the computer got from other input sources. And the computer tried to work with the data and kind of got overflowed with a lot of computations. The root cause actually was a hardware design error. So the power supply of the rendezvous radar was out of phase with the other power supplies. And so you might wonder that why the rendezvous radar was on anyways, because it wasn't needed for landing, of course. But they simulated a lot of missions and tried with the astronauts and everything. And in one of these simulations, they aborted the landing. They didn't have the rendezvous radar on, so they needed, after the abortion, to switch it on, because it's really critical to be fast. If you abort the landing, you have to go up, you have to go back to a moon orbit, so that you can dock with the command and service module and return safely to Earth. If you abort the landing and it doesn't work, well, you will be orbiting the moon until your air is depleted and you just die from suffocation, which was something the NASA wanted to prevent, of course, to televise. So from earlier missions, they learned, okay, we need to switch this rendezvous radar on so that if we need to abort, it's already switched on and we can make a safe rendezvous. And, well, you might say, well, the computer did everything right? Because we didn't make a rendezvous, we landed. So all the data from the rendezvous radar just didn't matter for landing. And that was the result of a, well, quite great design of this robust computer. And the team which wrote the software was a software development team at MIT, and the team was led by Margaret Hamilton. She even coined this term, software engineering, during the Apollo missions. And I think she's a great role model for all the women in computer science and technology. There are not so many in the audience, I think, but maybe with role models like Margaret Hamilton, we get more women in our industry. She was asked, of course, afterwards, so what were all these elements about? And, well, I don't read the whole answer, but it comes down to, well, works as specified. The computer did what it needed to do. Everything went well. The computer concentrated on the necessary tasks to land, and the landing was successful. There's another great story about Margaret Hamilton, because she was involved in the development of this DSKY interface as well. And there were really a lot of, or many hours during that time, and she sometimes took her daughter into the office because she had no childcare. So she let her daughter play with this DSKY interface. And then it eventually crashed. And Margaret Hamilton wanted to know why it crashed and how her daughter could crash that interface. She learned that her daughter had started the pre-launch program, which we started in the simulation, during the flight, so when they were already not on Earth anymore. And the software, well, it just crashed because the program during flight didn't expect this pre-launch button or this pre-launch command. So Margaret Hamilton thought, oh, well, that's not good. And she talked with her supervisors to get the time to prepare for these situations and to handle these errors. But they said, now, astronauts are highly trained, they are not your daughter. They don't make such errors, we don't need that. Well, happily, they did a lot of simulations, and in one of these simulations, quite the same situation occurred. A stressed astronaut initiated the wrong program, like Hamilton's daughter did. So then they got the time and the budget and the people to work hard to get this software as robust as possible to prevent a crash, which might have been deadly during landing or something. So always take human errors into account when you are programming. The design of the AGC proved successful with another example. I already told you that there was a digital autopilot, but that the astronauts could override it. 1 minute after the sequence I showed to you, so 1 minute before they actually landed, Neil Armstrong took a look out of the window. They had windows in this module. looked out of the window and saw a crater and rocks at the proposed landing site and said, oh, well, we can't land there. We're just going to crash on these rocks. So he took over manual control and slided above the lunar surface with these jets to an area without rocks. It was a digital autopilot, but the astronauts had always the last word and the control over the computer. So if you want to take a deeper dive into the AGC, the whole source code is published on GitHub some years ago already. So if you have spare time on the weekends or tonight, you can check it out. And I've just brought you one short example because it's assembly language and well, I don't even understand all the source code, but I brought you a short example with the first lines of the assembly code of the interpreter, so of the virtual machine. You can see there are some routines like a goto. I know it's considered harmful nowadays, but then it was a great help if you had only assembly language. And some branching statements, so if statements and higher level language elements and a call to subroutines and stuff. So just to show you that the interpreter was really a great achievement for the programmers which had to program the Apollo guidance computer and did not need to program everything in assembly language. So what did we learn? Well, I think the assembly language might be intriguing and the source code, but it's the methods and the principles which stay, I think. So the agile planning of the Apollo program, it wasn't called that agile at that time, of course, but still they had very clear goals for every mission. And everyone knew about the goals of the mission, to get the man into orbit, to get man onto the moon, and stuff. And I think it's great. And another part, the iterative design of the software, with every flight and with every simulation, the programs were optimized and thoroughly tested. And that's a great thing to learn always from simulations you do and to optimize your code. The robust design of the AGC and the fault tolerance of the software was also crucial, like I told you with the example shortly before the landing. And even if we don't program lunar landers, it's a good advice to follow. And of course, you had the vision of Kennedy and inspiring people like Margaret Hamilton who led this effort. Last point, without the rivalry with the Soviet Union during the Cold War, this might never have happened. We might not have reached the moon until today, possibly. And we didn't for the last 50 years. So after 1972, when the Apollo mission stopped, we didn't land on the moon again. There are missions now, the Artemis missions, but I think the next first moon landing isn't scheduled before September 26. And maybe the last method for all software engineers like you and me, abstraction and virtualization, which we see in this interpreter. That's a thing we find all over and again in the software industry, and it was a vital ingredient to the success of the Apollo guidance computer. In the keynote, Gregor Hoppe also talked about the right abstractions, and I think the short example of the interpreter showed that it's a good abstraction for the programmers. So that was my talk. Thanks a lot for flying with me through rocket history. In real life, I'm not at NASA, as I told you. I'm working as an architect and consultant in Germany at a consultancy just across the border. I hope you enjoyed the talk, and if you have further questions, you can connect with me via LinkedIn, or you can just ask them now. I think we still have 5 minutes left. Thank you.
All systems are nominal. Initialize Genesis sequence.